a historical advance for us and here in Brazil. So what I'm going to talk about is the first experimental implementation of an ion trap experiment here. So I'm not the first one who tried to do this, but it's like a curse in Brazil that never happens. So I'm hoping I'm the one who will do it. So currently I'm allocated at Federal University of ABC, at the Center for Natural and Human Science. So these are the main founding agents of Brazil. They helped me a lot, so I gotta thank them also. So first, let's just tell you where are the ion traps around the world. So mainly, we have 36 groups here in Europe, and 21 in the US, and another one's spread. But if you look at this map, you don't see anyone here in Latin America also, if you include Mexico. So the main goal of this experiment is to put us in the map. And also, what I know, just to keep you informed about Latin America, is that there's this group in Argentina from Christian Smigolo, who is also trying to put them in the map. So this is the picture of his experiment he sent to me. So it's an turbine ion experiment. So he's already also almost trapping ions. So where in Brazil, just to give you an overview when I'm allocated. So this is the city of São Paulo, and the city of São Paulo, what we call the huge São Paulo. That is composed of many cities, and this is the region of ABC. So ABC is because of these three main cities, Santo André, São Bernardo, and São Caetano. So, and then at Federal University, we have a campus here and a campus here. So this is the picture of the campus of Santo André, the one that I'm located in. And the university was founded in 2005, so it's quite new. And graduation started only at 2012, but we are already one of the top universities in Brazil. So the idea is to build a lab that it will act on quantum information processing with trapped ions. This lab I started in 2015 at USP under the supervision of Vanderlei Banhato, and also I had the help of Professor Daniel. And in 2018, I moved to UFABC, and in September, I moved my experiment, what I had, in São Carlos to Santo André. So, just a little bit of outline of the talk. I'm just going to talk briefly about trapped ions, the first ideas that I want to explore in this system, and the future experiments that will be really advances, so in quantum simulation. So trapped ions. This is the picture of trapped ions, not the ones that I want. No, they are mine, but from the time that I was in Innsbruck. So I want mine from the time that I'm here in Brazil. So why they are good for quantum information processing? Because they are robust systems. You have high operation fidelity. You can individually address them. You have short and long range interaction that they are showing recently. You have high coherence times, and you can do quantum analogs and inverse quantum computation. So they are really good systems to have here in Brazil, and to have all the theoreticians that are working in this kind of system to have a test bench for their theories. So it would be nice to have one of these in Brazil. So the kind of trap that I'm working with is a PO trap, an RF trap. So the idea is that you have 4 pairs of electrodes, and in 2 of them you put a constant voltage, and another one you put a RF voltage. And what happens effectively is that you have an harmonic potential that you can trap the ions, right? So, but the ion that I choose was strontium because of the transitions you can do with like simple lasers. And this is the picture of the trap that I have now. Is a ring trap based on a Davenant-Weiland design. And here is the RF electrodes and the DC electrode. The good thing about it is that you break the degeneracy of the 3 frequencies of oscillation because of this large electrode. So, but you gotta put this in vacuum. So I have Christian to go to São Carlos when I was there, and he helped me to assemble the vacuum system. This is what I was hoping to get, and this is what I got. So this is the system that is already in Santo André. So it's under vacuum. And right now what I need to do is to set up the laser system. But I'm not going to bother you with this experimental things, so I'm just gonna tell you about the first ideas that I wanna explore. So I'm gonna go on baby steps because I'm not ready to fully tackle quantum information processing. So the first idea is to study what I study a little bit in my PhD with atoms, which is a non-resonance to photon absorption. The idea is that you have two atoms that are interacting in the ground state, and they can be the same atom as it was in the case, and they have two excited states. So you shine a light in the middle of these two excited states, and the atoms can absorb two photons and go to the double excited state. So they do this because they can share the excess of energy of one photon to the other ion, and then they can absorb this. But the key ingredient here is interaction, right? So, and you can use this kind of thing to create entanglement. So if you have your two atoms fixed in space, and you shine this light, there you do the excitation, what you have is that you can have the first atom going to the F state, and the second one going to the E state, or the opposite. The first one going to the F, the E, and the second one to the F. So in theory, you can create like this entangled state. So this is not a new idea. So it's kind of a similar idea that is done in Entangled Rydberg atoms that was done in 2012 in the Philip Garnier group. So there they had two atoms in optical tweezers, and there they use Rydberg blockade to excite only one of them to the Rydberg state. So, and there they map this Rydberg state to other states, and they really did Bell state, and they show it there. So this is the idea. So if I have ions in a fixed position. So I have the double excited states. So what I first want to try to do is just shine light here and see if I see fluorescence. So if I see fluorescence, maybe I'm seeing this double excitation. So this is the first thing that I want to do. The second thing that I can do with this system is to wait if they go to this entangled state, and then they spontaneously decay, then since they have they are going to two different excited states, I'm going to have two photons with different colors. So I can separate them, detect them, and to do second-order correlations, and maybe see if we have some correlations, because this scheme is more or less like a Raman scattering. So, and recently I found someone who will help me with this, which is Marcelo França from Rio de Janeiro, and he's really interested in Raman scattering, so he said that we can just talk a little bit about it. So, but more advanced ideas from going from baby to fully grown. So when I have my system working, what I want to do is just I have some ideas. So normal carbon dynamics was a paper that Diogo wrote, and he put me in to help collaborate. So Fernando Simeão, which is also at UFABC, we are interested in control energy transfer, which is like a hot topic right now. Roberto Serra, also a theoretician, quantum thermodynamics, and Breno is a new professor also there, and we are trying to think about quantum networks to connect two photonic crystals to ions. So yeah, so thank you, and this is the team, and if you want to collaborate, you can be on the team. So thank you.
Yeah. Thank you very much. This is really a very good initiative.